All right. Nimadekwana.
Good evening.
How are you?
I'm good, and you?
I'm also good. Let's not waste any time. Um, as I've said, today we're going to cover a section of limits, another important section of calculus. Uh, so in this section, it covers limits which some we have done already under a method of first principle. So we are just going to extend from that. So I'll first give you a definition of the limit so that you can be familiarize yourself with the definition, and then from there I will then explain in detail with an example, and after even that we can then do as many questions as possible for limit. So the limits of a function is denoted by lim. Lim stands for limit as x tends to a, in this case, of f of a. So is the limit when x tends to a of f of a. So that's how we write limits. So limit of a function, in this case is function f, is denoted by limit when x tends to a. But now, the formal definition of the limit is the limit of a function is the value that a function tends to or approach. Some they use word approach, some they use words tends to, as a variable in the function. So usually we use variable x when it tends to a specific value. Normally on that one we use value a, and then here we use value x. So I will summarize this for you. So we have the limit. The limit of a function, in this case is function f, is the value that a function tends to, or the value that function approach as a variable in the function. For example, we can use variable x, which tends to a specific value for a. It's what we have here. Here on this definition, we are explaining what we have here. So as x tends to a, the function f of f will tends to f of a. So it means wherever we have a here, you just do the direct substitution. Because when f, in this case, when x approach a, the function f of x will approach f of a. So then now, why are we supposed to summarize in this way? Because you can see this is just a direct substitution. Where we have x, we just replace by a, then we have f of a. So the reason why we are summarizing this in terms of a limit is because of the example which I'm going to give you here. So you will see why we're supposed to use limits. So let's say we have a function of f of x in this case, which is equal to 1 over x, and we want to investigate the limits of that function as x tends to infinity. So we want to investigate the limit as x tends to infinity. What happens to this function as x tends to infinity? So this is what's going to happen. So the limit of function f when x tends to infinity. So the function f in this case it's 1 over x. So it means here where we have f, we can replace by 1 over x, and we have limit of x as tends to infinity of 1 over x. So limit as x tends to infinity, we're going to have a 0. So now the question is how are we going to get this 0? So it's what I'm going to explain to you of how are we getting a 0 when x tends to infinity. So let's do a table here where
Sir,
yes,
it's not visible.
or it's not visible this side, ne?
Yeah, because of the light. No, down there.
Oh, all right, okay. Now I see. So let me write this that side after the light. So we're going to have limit when x approaching infinity of f of x, which is the same as limit when x approaching infinity of 1 over x will be equal to 0. You can see that expression now, ne?
Yes.
All right, wonderful. So then now, on this side, I'm drawing a table which will help us to see that indeed when x approaching infinity, the value of the function f of x will be equal to 0. So now let's investigate that by having the values of x here and the values of f of x there, of which f of x is equal to, 1 over x. So we can choose the independent variable x here. So you can choose whichever variables you like. In this case, let's choose variable 1, and then we're going to use a spacing of 10. So it's 1, 10, 20, 30, 40. So for sure, there will be many values. But now let me jump some values in between here. And we have 100. And then from 100, we have 1,000. And then from 1,000, we have 10,000. So I jumped some values purposefully because we want to investigate when x approaching infinity, when this x increases from any number up to infinity, what happens to the function y? It's what we want to investigate because that gives us a background of the limit. So now let's start with 1 here. So when we substitute 1 where we have x, we're going to get 1 over 1, of which 1 over 1 for sure is 1. And then we substitute 10 because x in this case is 10. So when we substitute 10 there, we're going to have 1 over 10, of which is 0.1. You can verify if you have a calculator with you there. It's 1 over 10 equal to 0.1.
Yes.
All right, then now let's substitute 20. What is 1 over 20? We now substitute 20 there. What are we going to get if we substitute 20?
0.05.
0.05. And then let's substitute 30.
0.03333.
0.333. And then let's substitute 40.
0.025.
All right, then we skip some values here and then let's substitute 100. I believe in this one you're going to get 0.01, but verify with your calculator. All right, then let's substitute. If we substitute 1,000, is 0.001, right?
Yes.
And then we substitute 10,000. We have another 0 here. We're going to have 0.0001. Is that so?
Yes.
So now, we can predict with what we have here. What do you think we're gonna get if we substitute 1 million? What do we get if we substitute 1 million?
0,0000.
So there are many zeros. You see that?
Yes.
So let's see a trend here. In this case, X is increasing, right? X is getting bigger
Yeah.
and bigger. So when
Yes.
X is getting bigger and bigger, what is happening on the function f of X?
It decreases.
It's decreasing, you see that?
Yes.
And it's approaching certain value. So you can be able to predict just by seeing this decreasing. So when X is increasing, the value of the function is approaching which value here?
0.
Approaching a value of 0. That's very important. It's what is called the limits, because limits does not give you a definite answer, but it can predict. In order for us to find that indeed it's going to be approaching a 0 when it is approaching infinity, we must use the limit now. So you can see the answer we obtained there is 0. So this 0, we got the 0 from a trend that we have here. So we predicted from the trend, because there is no number which when you substitute, you're going to get a definite 0. A calculator may lie to you and say it's a 0, but in actual fact, you're going to get 0.00 something. There will be some numbers. But with that trend, you can be able to tell that it's going to approach a value of 0, of which that's where a limit appears. So when X is increasing, in this case, the function, it will be approaching 0, of which you can summarize by using a limit to say when limit of X approaching 0, so the function of X will be approaching a value 0, of which is just a matter of direct substitution. So where you have your function, where you have X in this case, you substitute that value, you will be given, and then you will get the output that we are looking for. So now I've summarized this of how limits work. So as I've said, the limit is just the prediction of what is going to be the final value on the function. So let's quickly go to the example so that you see how we apply this definition of limits in some form of questions you will be given. So here we're going to start with a simple question of limit when X approaching 3 of X squared plus 9. So we want to investigate the limits of that question. So how can we obtain the limit of this question? So we obtain, yes.
Your screen had frozen.
Oh, okay. So now I was busy with the, is it frozen now or it's fine?
No,
All
it's
right.
fine.
So we are now doing this question here on the board by applying the limits. So for sure, the question will say evaluate the following limit. We want
it froze.
All right. I think it's, is it fine now?
Yes.
All right. Whenever it froze, let me know so that I can change network, because I'm using different networks. As I was explaining, we are doing this question where we're supposed to evaluate this limit that is given there. And I've explained to you that a limit is just a direct substitution in this case. If X tends to 3, or when X approaching 3, so it means where we have X, we must substitute this value of 3 there. So let's substitute the value of 3 and see what we get. So, and you no longer write the limits when you do the direct substitution. So it means here where we have X, we substitute 3 and we obtain 3 to the power of 2 plus 9, of which will give us 9 plus 9, which is 18. So it's just a matter of substituting the value that you are given. So a direct substitution. So now let's go straight to the complex questions where we are not supposed to just do the direct substitution like what we have there. Because there are some questions which we are not required to just do the direct substitution. So let me find those questions for you just now. I picked questions from previous question papers so that we can be consistent with what can be said in the exam or in the tests. All right, so this is the question. It's question number B. So we want to evaluate the limit when x approaching 2 of x squared plus 4x plus 4. And then all this divided by x minus 2, or we have a negative here. So this is the question we have on the board. So limit when x approaching 2 of f of x squared minus 4x plus 4 divided by x minus 2. Can you tell me what is our function on that question? What is our function?
The parabola.
So we are given parabola on the numerator, and on the denominator, what is it?
A straight line.
That's a simple straight line. So now, so it means f of x is given by this whole thing. So it's x squared minus 4x plus 4 divided by x minus 2. So let's do direct substitution and see what we obtained here. So when we do direct substitution, can you tell me the answer we're going to get? Like what we have done on the first question. So let's do the direct substitution and then you tell me the final answer we're going to get if we do the direct substitution.
Zero.
You get an answer of 0.
Yes.
All right, let's check. On the numerator, what is the answer you're getting on the numerator?
Zero.
And then on the denominator, what answer do you get on the denominator?
2. It's a 0.
It's a 0. So it's 0 over 0. Any number divided by 0 is what?
It's 0.
Any number divided by 0. Let's take for an example, 10 divided by 0. What is 10 divided by 0?
Oh, it's undefined.
Yes, so whenever you have a denominator of 0, you have a situation where you have an undefined answer. So that simply tell us that direct substitution does not work in this situation. And it's what I'm interested to guide you through. So now we must know what to do whenever we come across this situation where we have an undefined answer. So we don't just rush to conclude that is an undefined answer. So this is what we're supposed to do. So we'll have to simplify this before substitution, like what we have done from the first principle. So we need to simplify further what we are given as a function there. So let's simplify and see what we obtain in this case. So we're going to have limit when x approaching 2, then we have to simplify or to factorize the numerator. So the factors of the numerator would be x, 2, and 2. Therefore, one must be positive, both must be negatives in this case, in order to get x squared minus 4x plus 4, and then divided by x minus 2. So we just factorize the numerator. So after factorizing the numerator, you will see there are terms which are canceling to each other. And when some terms are canceling to each other, what will you be left with then if you cancel some times together? What are you going to get? So x minus 2 can cancel with x minus 2, and you're left with what?
X minus 2.
We left with x minus 2. Very true. So that is what we're looking for. Then after having that, you can then do the direct substitution. So of which, where we have x, we can substitute 2. So we're going to get 2 minus 2, which gives us an answer of 0. So that is how we attend to these questions, where before we do direct substitution, we first have to simplify. Then after simplification, it's when you can do the direct substitution. So you must get this right because it's very important. So I'm going to do another interesting question before we focus on the questions, which I will need some for you to do some of them. And we can also do as many questions as possible under differentiation by rule. So this is question number 3, where we are finding a limit when x approaching 3 of x minus 3. They love this question very much, divided by root of, it's approaching 9, sorry. So yes, approaching 9x minus 3. So this question is very, very popular. So now let's attend to this question and see what we obtain. You can see we have a root here. Eh? When we do direct substitution, what are we going to get? If we do direct substitution, so it means when we have x, we'll substitute 9, right?
Yes.
And we'll have 9 minus 3, which is 6. So we have 6 on the numerator, and then on the denominator, what are we going to have on the denominator?
0.
It's 0. Do you see direct substitution does not work in this situation?
Yes.
So whenever direct substitution is not working, so it means you have to simplify this. And the simplification of this is not easy as we may think. So we have to do what is called rationalization. So let's rationalize this expression. So we're going to have limit when x approaching 9 of x minus 3, all divided by root of x minus 3. So this is what we do when we rationalize. We must take the denominator that have the root and then change the sign. If we have negative, it means we're going to change it to positive, and we divide by exactly the same expression. By doing so, we have done what is called rationalizing. We have done a question for rationalizing yesterday. So we take the denominator and then we change the sign of that. We have root of x plus 3 divided by root of x plus 3. So that is what is called rationalizing. It's a special one. After having a special one, we can then manipulate this, and it's going to give us 9 there, and then on the numerator we're going to have x is x minus 3, and then there is a root of x plus 3, all divided by root of x minus 3, root of x plus 3. Are we all together up to that stage?
Yes.
All right. Then after having that, we don't need to rush in disturbing the numerator. So we can just write the numerator as it is. And then the denominator is the one we want to deal with because it's the one with problem. It's having a denominator of 0. So we rationalize and then we multiply root of x and root of x. Multiplication of root of x and root of x is going to give us what? It's going to give us x, right? So let's go to the middle.
Yes.
So on the middle terms, because here we have negative and then we have positive, and these are the same terms. Can you tell me what is going to be our middle term in this case?
It's 0.
It's going to be 0. That's very true. And then that will mean on the other side, we're going to negative
-9.
negative 3 and what? And positive 3. So we get negative 9. Are we together?
Yes.
All right, wonderful. So after having that, then we can then simplify this further by having a limit when x approaching 9 of, and then this we can write as, okay, so let's simplify the denominator, x minus 3 root of x plus 3 divided by, then the denominator we can write as x minus 3 minus 6, like that. But we are interested to the 3 there, so it means we're going to have limit when x approaching 9 of x minus 3 root of x plus 3 all divided by x minus 3 minus 6. So we did not violate any rule there. So we just put this into brackets because we're interested to that term. So then after having that, we can then do the direct substitution. So it's only when direct substitution and simplification is not working where we can agree that it's going to be undefined. So now let's do the direct substitution and see what we're going to get on the denominator. So let's substitute 9 on the numerator. If we substitute 9 where we have x, what are we going to get on the numerator then? So you can use calculator. You substitute 9 where we have x on the numerator. What are we going to get?
Sir.
Yes.
So what did you say?
All right. So I was saying, in this case, we can then do direct substitution just to find out if this is going to give us the answer we are looking for. So let's do the direct substitution. Where we have x on the numerator, we substitute 0. We substitute 9. Where we have x, we substitute 9 on the numerator. What do we get if we substitute 9 on the numerator?
36.
We get 36 on the numerator. And then on the denominator, what do we get? We substitute 9 on the denominator. What are we going to get? So it's 9 minus 3 minus 6.
0.
It's 0. So it's 36 divided by 0. So it's in this situation after simplification where you can conclude that this is undefined because it was not simplifiable. We tried 2 approaches. The first approach is for direct substitution, of which after doing direct substitution, we don't need to conclude in that case. We need to go further and rationalize. You simplify or you rationalize. Then after rationalizing, when you get an expression with a denominator of 0, then you can then conclude that this is undefined. So then now let's go back to do questions on, differentiation by principle. And we also focus on questions for limits. So I have many questions on my phone. The first question we're going to do together is this one, where we have a question which requires us to determine dy over dx. I believe you remember this notation, right? Of dy over dx.
Yes.
All right.
Yes.
So then now the first question there, we are given y equal to 3x squared plus 6x is cubed here. X squared plus x minus 4. So before I do this question, I want you to try and do the question. When you are done, you send the solution to me and I see if you get the correct answer. So you have to do the first one. The second one we're gonna do at later stage. For now, focus on the first question. Can you do the first question? And when you are done, you send me the answer. From there, we're gonna do correction if you did not get it right. So it's now your time to do that first question. We want to determine dy over dx. All right, I can see the solution you sent there. Let's do correction for that question, right? we have y equal to 3x cubed plus 6y squared plus x minus 4. Like what I told you yesterday, that situation, it requires us to use derivation by a rule where if we are given an expression in that form, we need to derivate. To show that we have derivated, we write dy over dx equal to, then the derivation on that case is going to be a multiplied by n, and then on the exponent we subtract 1. So that's the rule we're supposed to use in order to derivate this. So let's apply the rule and see what we get. So we're going to have dy over dx. This is just to show we have started to derivate in this case, which is equal to, then here, when we derivate the first term, it's going to give us 3 multiplied by 3x to the power of 3 minus 1. We applied that rule we have there on that expression. So it's 3 multiplied by 3, 3 multiplied by 3, x to the power of 3, and then we subtract 1. So we do the same on the second term. So it means we're going to have 6 multiplied by 2, x, and then on the exponent we subtract 1. And then on this one, we're going to have 1 multiplied by 1, x, 1 minus 1. Because this 1 here, then that one you subtract with 1 from the principle or from the rule. Then 4 is a constant. We talked about a constant yesterday. A constant is a number without a variable next to it. Like here you can see we had variable x, we had variable x, we had variable x. But here is just a number. So if it is just a number, it means that is a constant. So whenever you have a constant, you must know that the derivation of a constant is equal to 0. And I explained yesterday why it's equal to 0. It's because if it's just a number, it means it's multiplied by x to the power of 0, of which when you multiply 0 with 4, it's going to give you a 0. Are we together?
Yes.
Yes. So here, whenever we are derivating a constant, you must know it is 0. Therefore, we don't have to write anything. So let's simplify and see what we obtain. So it's 3 times 3 will give us 9x, then 3 minus 1 is going to give us 2, plus then here is 12x to the power of 1, plus, and there is 1 minus 1, which is 0, x to the power of 0 is 1. So that is the final answer we're supposed to get on this question. So it's 9x squared plus 12x plus 1. Did you see how we get to that answer?
Yes.
All right. Can we do question number B?
Yes.
All right. We have yx minus y equal to 2x squared minus x. So on that question, we are not supposed to just substitute or to apply this rule, because you can see y is not the subject of the formula there. So let's first make sure y is the subject of the formula. We simplify first before we derivate. So the simplification we're going to do in that case can be to take out the common factor if it's there. So let's take out the common factor in this situation. Let me verify if I copied the question correctly. For in case, all right, here there's no these two. As I was saying, we're not going to get to the answer if we have that 2. So it's x squared minus x, and then on the left hand side is yx minus 1. So we have to take out the common factor of y. So when we take out the common factor of y, we're going to have x minus y.
Your screen just froze.
Sorry? Oh, the internet. Ne?
Can you repeat? Yeah.
Let me repeat here. We take out the common factor. We take out the common factor of y. So when we take out the common factor of y here, we're going to be left with x there. And when we take out the common factor of y here, we're going to be left with what? With 1. So hence we have y at x minus 1. It's because after taking out the common factor, we left with x here and we left with 1 there. Is that clear?
Yes.
All right. And then on the other side, we do the same. We take out the common factor of x purposefully. So when we take out the common factor of x, can you tell me what are we going to be left with on the first term?
X multiplied by x minus 1.
Yes, minus 1. Very true. What do you think will be the next step in that case?
To divide by x minus 1.
Very true. We're going to divide both sides by x minus 1 here, and we divide by x minus 1 there. So it means we're going to be left with y, which is equal to what?
X.
Which is equal to x. Remember, we haven't derivated as yet, ne?
Yes.
We were just making this y the subject of the formula. So hence you see, we haven't introduced dy over dx. It's because we haven't derivated. But since the question requires us to derivate, then we can now derivate because y is now the subject of the formula. Is that clear? So
yes.
the derivation is going to give us dy over dx. Can you tell me the answer we're going to get when we derivate that simple equation?
One.
We are going to get an answer of 1. As simple as that. We're going to get an answer. Are we together on that question?
Yes.
All right. There's this other question I want to do with you, but you will have to try it first so that I see if you are getting this right. So the question requires us to determine. We want to determine dx of x squared minus 2x minus 3, all divided by x plus 1. So this is the question which I want you to do just now. Let me give you 3 minutes to work on that question. I'm giving you 3 minutes because it's saving 3 marks. All right, all right. I can see the answer you sent just now. Let's do a correction for these together. Remember, we apply this rule when an expression is in polynomial form. So let's see what we supposed to do on this question there. I told you yesterday about this notation, that this notation, you keep it before derivating, and then you leave it only after derivation. So it means when you do your simplification on this expression, you keep that notation. It's only after derivating where you leave it. Is that okay?
No.
All right, let me explain again about the notation. So this notation, you keep it, you have to keep the constant, I mean the notation before any simplification. I mean before any derivation, you keep the notation. But immediately when you start derivating, you no longer write the notation. Let's do and see so that you see what I'm talking about. So this notation, we're gonna keep it because at this stage, we're not going to derivate because we can't apply this rule. We can't apply this rule when an expression is still in fraction form. So we must have to write it in a standard form. So this is a standard form. So we can write it in a standard form only if we simplify this. So let's factorize the numerator. So the factorization of the numerator is going to give us x here and x there. So it's going to give us 3 there and a 1 there. So here is negative and there is positive. So we divide by x plus 1. So you can see there are some terms which are cancelling there. So which terms are cancelling?
X plus 1 and x plus 1.
Yes, and then when those terms are cancelled each other, we're going to be left with x minus 3. Do you see that?
Yes.
You can see the notation is still there. The reason why I'm keeping the notation in this case is because I haven't derivated as yet. I haven't derivated as yet, hence I'm keeping the constant. So what I've done here is just to simplify. I've just simplified this expression that we are given there. So then from there, we can then derivate because it's in a simple form. It's in this form where I can apply the rule. So let's derivate and see what we obtain. So this is having an exponent of 1. So when we derivate x to the power 1, it's going to give us 1 x to the power of 1 minus 1. What is the derivation of negative 3?
0.
It's 0, yes. So it means here we're going to be left with x to the power of 0. 1 minus 1 is 0, hence we have x to the 0. And the answer of any number to the power 0?
1.
Is 1. So this is how we deal with these questions. This is how we deal with this notation. You must,
So
yes.
when we have a fraction, we have to first factorize.
Yeah, we first simplify. It's either we factorize or we simplify. We do those two things. Otherwise, we are not allowed to apply the rule when we still have a fraction. We first have to factorize or we simplify. Is that okay?
Yes.
Yeah. In all questions, you must first do this. You must first simplify before you derivate. And one of the important things which I'm emphasizing on this equation or on this question is the notation. We must know how this notation works. So the notations we used before is not the same with the notation I used now, and they work in different ways. So this one you must keep before derivation. And once you derivate, you then omit that notation. But on the different notation, when you simplify, you don't write the notation, but once you derivate, that's when you're going to introduce the notation. So they work in a reverse way, in a different way. So, but I believe we still have to do as many questions as possible. But at this time, I'm going to give you a homework. So I'll send the homework on WhatsApp, which you must do and send back to me. And then at later stage, after my class, because I'm going to another class immediately after this one. So after I finish, I will do correction and then send the solutions to you. Is that okay?
Yes.
All right. Otherwise, for today, let's stop here and have a good night.
Bye.
Bye.